So in this first module of the lecture, we're going to look at the basic concepts of vectors. But before we do that, I'd like to ask you a bit of a question to kind of emphasize why vectors are so important within the physical sciences and naturally engineering. So imagine that you told me that you walked out your front door right now and you took 15 steps. From that information, would I be able to know where you necessarily ended up? And hopefully you see that the answer is no, because maybe you took 15 steps directly perpendicular out your door, or maybe you took them at a 30-degree angle in the clockwise direction, or maybe a 30-degree angle in the counterclockwise direction. Just based upon that information alone of knowing how far you went or the distance you traveled, I wouldn't have kind of the complete picture. I wouldn't have unambiguous information to know what is known as your total displacement. And that's why vectors are so important in the physical sciences, particularly that example that I just gave you is within the study of kinematics in order to be able to describe physical quantities that are unambiguously described, meaning you only get the whole picture if you know both the magnitude and direction. So hopefully that made a little bit of sense to you. In terms of when you get to the end of this video, hopefully you will be able to describe the two key characteristics of a vector. Also, I hope that you'll be able to identify different examples of vectors in the physical sciences. I just gave you one, that concept of measuring how far an individual or a particle or anything moves from one place to another over an interval of time is known as displacement, and we'll talk about some others as well. Hopefully you'll know all the common notation of vectors like anything in engineering, because we borrow from math and we borrow from science, in this case physics, and we invent our own stuff sometimes. Oftentimes one of the most confusing things is just being able to sort through all the different notation that you see. And in addition, the last thing that I want you to know is how to be able to change the magnitude of a vector, which we'll see is one of the two key characteristics mentioned in bullet 1, by multiplying it by a scalar, which you remember hopefully from the first portion of the engineering math lecture. Scalar is just a fancy word for number. So let's introduce vectors. So vectors are quantities, physical quantities, that are unambiguously described, meaning you need to know both their magnitude, which put simply is how much or amount, along with their direction, which put simply is kind of the orientation, or maybe direction is even a clearer word to understand. So any physical quantity that's described by both a magnitude and a direction is a vector. Now, naturally, helps if I go the correct way. I kind of gave you the example of displacement being a vector at the beginning of the lecture. If you think about an individual starting here and maybe going there, naturally they travel a certain distance, but in addition, there's a certain direction or orientation to the way that they travel. And without knowing that direction, you really don't know where they ended up. So what other physical quantities are fully described by vectors? Well, it turns out, for those of you that are kind of beginning to explore calculus, that any time derivative of displacement is also a vector. So the most simple time derivative of displacement is the first derivative. And if you're not familiar with what a derivative is from calculus yet, that's okay. Let me kind of get to the end and then I'll walk you back to a physical understanding. But the first derivative with respect to time of displacement is velocity. And velocity is a quantity that any of us that are like me heading out to drive here in a few minutes are very familiar with, because it just measures the rate of change of the position, which we probably have a better intuition of just knowing is speed. But again, imagine that you have your cruise control locked in your car and you're going 40 miles an hour, right? That is an example, maybe that's very slow, but that is an example of a magnitude of a velocity. Which way are you actually going? Which way is your displacement changing? You don't know from that magnitude alone. And that's why speed is nothing more than the magnitude of the velocity vector. But in order to fully understand it, you need a direction as well. And not surprisingly, if I look at the rate at which my velocity is changing, which is known as my acceleration, which is just how much I'm speeding up or slowing down and in what direction, that's a vector quantity as well. So the three basic vector kinematic quantities are displacement, velocity, and acceleration. There are other examples of actual vectors within the physical sciences. The one that we're going to see when we move on to mechanical engineering and we do our lab is the idea of a force. And just think of a force as anything that tends to change the actual velocity or speed of an object. So if I push on something, generally speaking, that will change the speed of an object. In addition, when the Earth exerts a gravitational force on this can, that is a quantity that's described by a vector. There's a certain amount or tendency to change its speed. We'll talk all about that when we get to Newton's second laws. And the direction is pointed towards the actual center of the Earth. So when you think about how to actually show vectors graphically, naturally arrows are a great tool to use in order to describe vectors. Well, why? Well, think about if you drew any arrow. Naturally, you have to decide two things. Imagine you start at this point. You have to decide how long to draw the arrow, and in addition, you have to decide which direction to draw the arrow in. So naturally, the geometrical parameters of an arrow are perfect for actually describing the two quantities of a vector, or magnitude and direction. So when I visually have an arrow used to describe a vector, the length of that arrow will correspond to the magnitude. Now, if you think about it, think of the example of force I gave you. A force is measured in SI units of newtons, which we'll talk about in the mechanical engineering lecture. So when I draw an actual arrow, it's going to be measured in a unit of distance, or even more simply, we talked about velocity being represented by a vector quantity. When I draw an arrow, its length is physically measured in distance. So the idea is that it's proportional to, I have some sort of scaling factor that kind of maps back to whatever the units of that physical vector are. But the length of the vector represents its magnitude, and the orientation represents its direction. Now, we're engineers, we like to put numbers on things. Naturally, it's easy to measure the length of any arrow, right? You can just take out a ruler, but in order to quantify or measure the direction, you really need some sort of reference axis by which you can measure an angular displacement. Then we'll look at that a little bit later. But one thing I wanted to get to you in terms of the terminology of vectors, if you think about when you draw an arrow corresponding to a vector, you have a point at which you start and you have a point at which you end. And the point at which you start, you traditionally note by a dot, and the point at which you end, you denote by an arrowhead. And the vector is assumed to go from the dot to the arrowhead. So the terminology that's actually used in vectors is the idea of a tail. The tail is the part at which it's the point at which it starts, and a tip. So there is the tail of this vector is positioned at point A, and the tip is positioned at point B. Second question, what is the meaning of this kind of variable A with a half arrow over top, or in this case, a full arrow? Well, we're going to be working with vectors mathematically. And whenever we work with a quantity mathematically, it's good to have variables to represent them. So just like standard variables of scalars, we can have variables that represent our vectors. We're going to pick letters from the alphabet for our variable names, maybe something like A. But to let someone know that it's a vector, we're going to write an arrow over top. However, know that if you're reading in a textbook, they might choose to actually bold the variable name of the vector in order to let you know that it is in fact a vector. Now, what if I take a notation of a vector, like A with an arrow over top, and I put what looks like absolute value signs around it? So if you think back to lecture when we covered the first part of engineering math, we said that if you had a variable name corresponding to a matrix and you put absolute value signs around it, it meant the determinant. In this case, when you put absolute value signs around the vector, that means the actual magnitude of that vector. And if I put an angle sign in front of the vector name, that means the direction of the vector. So this is just math notation to get if you have a vector A arrow over top, how you write the magnitude and direction. And question, are people nice enough to pick a consistent notation for this, having the little arrow hat versus bolded? The answer is no, unfortunately, just like anything. So one thing we're going to see in the totality of this lecture is that there are two different ways in which we can write or describe vectors. The first that we're going to talk about is polar form. And the reason that we're going to talk about polar form initially is it maps up very well to the natural description of what vectors are. So remember, vectors are anything that are defined in terms of a magnitude and direction. So polar form just puts two numbers behind those two quantities. And how would we actually see that? Well, imagine you have a vector and it has a tail at O and a tip at P. And imagine you set up an X and Y coordinate system and made the origin of that coordinate system right at the tail of the vector. Naturally, you can measure the distance from the origin to the actual tip of the vector, and that would be nothing more than the magnitude. That's a number that we can put on it. But the nice thing about putting the tail of the vector at the origin is now I can also measure the angular displacement from any reference axis. We remember that in the physical sciences, we'll typically choose the positive x-axis as our reference. So if I have a vector here in the first quadrant, I can just measure the angle in the counterclockwise positive direction. Again, that's just a convention as well. And I'll call that angle the actual direction of the vector. So this is the Greek letter phi. So this particular vector, it has a magnitude of r and it has a direction of phi. So I can put two numbers behind the two basic fundamental quantities of that vector. In addition, you're kind of getting a little bit of foreshadowing here of how you can use right triangle trigonometry. Note that if you go in a two-dimensional coordinate system from the tip and you drop a perpendicular line to the x-axis, you naturally form a right triangle, and you can compute the lengths of these bases of the right triangle pretty easy. And from that, we'll see that that's going to go foreshadow to our next form of vectors. But key points that you want to get from here is we're going to measure the actual magnitude of the vector as the distance from, if we create an XY coordinate system, put the tail at the origin, it's the distance just from the tail to the tip. And the angle will always be measured from the positive x-axis to the actual vector with a counterclockwise positive convention. And hopefully everyone gets what I mean by that. What I mean by that is you could go from the positive x-axis and go in the clockwise direction, and you would get a very, very large angle that is actually, if you add the angle I'm showing and that angle, of course, it would sum to 360. But by convention, you move from the positive x-axis in the counterclockwise direction. So that's how that is being defined. What we're going to see when we actually get to the rectangular form of vectors is that these lengths measured along the x-axis and y-axis that result from dropping the perpendicular are known as actual components. So what we're going to find is the only math we're going to need in order to do all this, and it's not coming in this mini lecture, but it's coming later on in this PowerPoint, is right triangle trigonometry. So hopefully everyone remembers. If not, you'll get just what you need in time as we do the examples. That in right triangle trigonometry, so first and foremost, a right triangle is just a triangle with a right angle inside. And the side lengths are related by a formula that's known as Pythagorean's theorem. Namely, the side length that is opposite of the actual 90-degree angle, it will be the largest. If you square whatever the length of that side is, that is equal to the sum of the squares of the other two side lengths. That's the idea of Pythagorean's theorem. In addition, think back to wherever you might have seen functions like the sine function, the cosine function, or the tangent function. Maybe you've heard the acronym SOHCAHTOA. What that's basically saying is if you have an angle in a triangle, you can naturally define sides that are both opposite and adjacent to that angle. So for example, angle A, which I'm measuring with the capital A, the opposite side is lowercase a, and the adjacent side is B. So I can take the ratio of those two side lengths and I can relate them to a function, and just think of it for now that I can use a calculator that I can compute on that particular angle. So we'll go over all of that a little bit later. But what is the idea of vector scaling? Well, what does it mean to actually take a vector and multiply it by an actual scalar? Well, all that is going to do is change the magnitude of the vector as long as the actual scaling constant is positive. So if I multiply by a scalar k, if I multiply a vector a rather by some scalar k, and k is a real number, that's what this notation means. K is an element of the real number. As long as k is positive, it is going to have it's just going to change the magnitude of the actual vector. If k is greater than 1, it'll increase the magnitude. If k is less than 1, it will scale it down. So let's actually look at some examples.